Embark on a journey of inspiration and discovery with the Purdue Lecture Hall series, proudly presented by the Purdue Institute of Inflammation, Immunology, and Infectious Disease. Join us as we delve into the remarkable odysseys of these aspiring scientists, each crafting their own narrative in the world of science and groundbreaking research. Take a glimpse into their diverse cultural backgrounds and the journeys that brought them to Purdue University. Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel. Welcome, everybody. My name is Tommy Soares. I'm Director of Scientific Strategy and Relations for the Purdue Institute of Inflammation, Immunology, and Infectious Disease. And today on our Purdue Lecture Hall series, I have the pleasure of welcoming Trung Thach, completed his Ph.D. in structural biology in Korea in 2015 and subsequently served as a research professor at Korean University. In 2017, Dr. Thach, he joined the Pioneering BioNano Center and later became principal scientist funded by the Brain Korea Fellowship, the National Research Foundation, and Imnewrun BioSciences, focusing on CRISPR research. Since 2021, December 2021, he has been working as a postdoctoral researcher here at Purdue University under the supervision of Dr. Leifu Chang and Dr. Ramaswamy Subramanian from the Department of Biological Sciences. And it's really a pleasure to be able to welcome Dr. Thach to this program and to watch him do this transition to Purdue University in continuation with his commitment to cutting-edge scientific research. Welcome, welcome, Chang. Thank you so much for taking time to talk to us today and sharing some of your journey with us.
Yeah, thank you, Tommy. So I'm gonna share my slides.
Okay. Go for it, as we typically do.
Here is it.
Okay, let's see if we do.
So, can you see it?
We can see the slides. If you want to do the full screen, there you go. Perfect.
Yes.
Take it away. Thank you, Trung.
Okay, thank you, Tommy. Hi, everyone. My name is Trung. I'm a postdoc researcher in Ram's lab currently in Purdue University. So today I'm gonna talk about atomic structure approaches. Hopefully, after my talk, you have some idea what the protein structure look like. So, but first, I would like to introduce myself a little bit. I would say I am a researcher. To me personally, researcher is a person search something new, research, and then research something new. Of course, it's in not repeating progress. It's a spiral structure of professional development. It's including 3 stages. First, search something new idea, new techniques. And then you test it by communication, by reading, by experiment. You test whether the idea is negative or positive, whether new technique is good or not. And after search and test, you will learn from it. You learn new knowledge, you gain new experience, and then you back to search. This is a kind of professional development, at least in my personal. So I come from Vietnam, but I was educated in South Korea. So here the views of my previous campus through my office in the last winter before I'm leaving Korea. And as you see here, they have a building. A building is called Samsung Library. So this is a photograph I took in first semester I was in Korea. So after graduation, I was appointed as research professor in Korea University for 2 years. And then I back to my university with a grant I got from National Research Foundation and Brain Korea Fellowship. I work in BioNano Center, the building here. And then I was appointed as principal scientist as the office in here and center. So I used to commute between this building and this building. Was waiting for new building was constructing. We call C&S Center building. And after that, our family decided to move to America, and Purdue is our destination, where my wife working as a senior scientist in nanotechnology institute. I continue my research in structural biology lab. And when we talk about structural biology, so today I would like to bring some knowledge to use about the structural biologies. So firstly, I would like to share the relative size of the objects from the human to atom. In the human size scale or chicken scale, you're able to see by your naked eyes, or you can easily just take a photograph using normal camera. But smaller than that, for example, animal cells or mitochondria, you're not able to take a photo using the normal camera. What you use is we call light microscope. And light microscope with a magnification of 40 or 100 magnification, you're able to see clearly animal cells. But smaller than that, for example, protein, lipids, or atoms, you just use something we call giant machine or a giant microscope. This is electron microscope. It's sophisticated machines as tall as 2-floor buildings go along with many suppliers. So now the concept is to see or to photograph a small molecules like protein. We need a giant microscope, a giant machine. Talking about the proteins, you may know protein structure come from amino acid. It's an amino acid connect together. It's from the polypeptide chains. And polypeptide chains is primary structure. When amino acids interact each other, they form secondary structure. For example, in here, the alpha helix. And alpha helix or secondary structure, they fall in 3D. They interact each other. They form 3D structure or tertiary structure. And in many cases, 3D structure or protein molecules they assemble together, or they make a complex of the protein molecules. We call the quaternary structure. So when we talk about the protein structures, in many cases, we mention about the 3D or quaternary structure proteins. So today I would like to talk about how to capture or build a protein structure in 3D, 3 dimensions. So first, if I mentioned earlier, we need a giant microscope to capture protein structure. And this one we call electron microscope. And a technique to capture protein structures using electron microscope is we call cryo-EM, cryogenic electron microscopy techniques. For a decade development, with a lot of contribution from different scientists, the cryo-EM in structural biology got award for Nobel Prize in chemistry to 3 key contributors, Dr. Dubuches, Dr. Frank, and Dr. Henderson. So for their contribution in development of cryo-EM in structural biology. And nowadays, cryo-EM is really revolutionizing structural biology. So how can we do cryo-EM for protein structure? So as I mentioned earlier, we have to put the protein sample into the giant microscope. So first, we have to prepare the cryo-EM sample. So to prepare cryo-EM sample, we had to prepare we call cryo-EM grid. Usually it made from gold or copper or another materials. And this look like how cryo-EM grid look like. It has a lot of square inside, you can see. And when we zoom in one square, it has a lot of hole. And when you apply protein sample on the grid, the protein solution will enter into the holes and we capture inside the hole. When we zoom in the hole, as you can see, the hole size is quite small, right? It's around 1.2 or 1 micrometer. Of course, micrometer still super large compared to protein molecule size. So one square, you have the protein inside. And when you zoom in the hole, you can see how protein look like. It's in cryogenic temperature, protein is frozen, and it's trapped in different orientation. And in different orientation, it reflects for the protein molecules. And when in the cryo-EM, we can take the picture of the different orientation of protein molecules. For example, look like this. We have different orientation of protein molecules. And in cryo-EM, we photograph the 2D photograph reflect for different orientation of protein molecules. And how it look like 2D like this, a square, rectangle, for example. And you see the final photograph of the proteins molecules from cryo-EM. We call 2D micrographs. And for example, in here, grow EL protein, with the size around 1 to 5 nanometer in the different orientations of the molecules. So you can see different 2D graph. Where this is a circle, this is like rectangles. And now our point is how to build the 3D structure of proteins from 2D micrograph like this. Just I will show you principle right now. For example, like images, we have 2D photograph in different views of a house. And in here is a different size, different orientation of a house in 2D photograph. The next step is what we do is we have to classify different classes of the view. So for example, in here we have 3 classes reflect for different view. For example, top view, side view, and front view. So now we have the 2D views of the house. What we do next is we just merge all 2D together to have the 3D map, 3D information of the house. It has the top information, in front information, and side view, side information. So we have 3D map of the house. A similar concept to proteins. We have 2D macrographs. And with the different macrographs, we have a lot of different orientation of protein molecules. And what's next is we classify to get the 2D views of the protein molecules. For example, in here, I show you it's our all protein in our research. You have the side view, and they also have the top view. And here you can realize you have different view of the proteins molecules. And what next we do is we convert 2D views to 3D map. And here's how 3D map look like. This is we call cryo-EM map or electron density map. So in here, the 3D maps they have different side view. I show here, it reflects from the 2D classification. And then also you can see it has a top view as well. Also exactly reflect from the 2D classification. So normally 3D map it will constructing from the 2D information. So we call electron density map. And because from 2D to 3D, it requires a lot of resources, especially computational resources. So we need a superpower computer to process from 2D to 3D. And our 3D is electron density map. Just the basic concept in electron density map is you have the atom, and it's an atom, you have electrons. The electron is they form the map surround the atom nucleus. So when you know the electron density map, you definitely know which the atom is. And for example, now you have electron density map of the proteins. When you zoom in, for example, you can see how electron density map clearly look like. And then what the next step is, do something we call computational work. To me, it's like a scientific game. You wear 3D glasses and play the atom or amino acids into the electron density map. For example, in here, what we have electron density map, and we play amino acid into this electron density map in the atomic level. For example, you say oxygen is a carbon, and the blue one is nitrogen. So in the different atomic level, you can build the electron amino acid in electron density map. And now you have information of electron density map. You just follow electron density map information and continuously build amino acid by amino acid in atomic level. And until you can finish the whole electron density map. And for example, in here, you can see it's a tyrosine. And the point is, we have all electron density map information. We have to build all amino acids or atomic inside the electron density map. For example, like this, we continuously build into the electron density map what we got from the cryo-EM, for example. And in the end, we have fully amino acid in atomic level fit right into electron density map we got. And this is we call protein structure. And at the end, for example, in here, I show you, we have cryo-EM structure, a P2H receptor in atomic level. This one is the map, the electron density map of cryo-EM map. And reflect after we built, we have 3D structure of P2H receptor. This is side view. And this one is the top view. And as you see in here, the receptor has 3 molecules of proteins. 1, 2, 3. So each trimers, or in earlier I mentioned, is a quaternary structure, right? It has the 3 molecules of protein assembled together to form a receptor. So this is a cryo-EM structure. So what if proteins are too small to capture using cryo-EM? Sometimes your protein of interest is so small, the photograph is not clear enough, it blurs. So it's not able to use cryo-EM to see the protein structure. So we have another technique. It's a protein X-ray crystallography. Yes, you may know about the crystal. So as the name is, we must have protein crystal. Of course, you can imagine how crystal look like because crystals are everywhere. For example, the principle of crystal is molecules are highly organized or same orientation. And you may see a lot, especially when you live in Michigan in the winter. For example, this one. This is snowflake. It looks beautiful, isn't it? And snowflake actually is an ice crystal. And the snowflake made from water. As you can see in here, snowflake has 1, 2, 3, 4, 5, 6 hexagonal shape. Even though in this photo, you can see different snowflake, but they do have 1, 2, 3, 4, 5, 6 hexagonal shape. The principle of the hexagonal shape of the ice crystal or snowflake is the way water molecules packing to form a snowflake. It has the 1, 2, 3, 4, 5, 6 water molecules packed in hexagonal and repeating its same orientations. So in certain conditions, the way water packing will form the ice crystal or snowflake as you see. A similar concept to protein crystal. We have the protein, small molecules, you're not able to see by cryo-EM. It's for example, it's a size of 0.15 nanometer. So we have to crystallize it. And in the certain condition, this protein can be crystallization. So it's from the protein crystal. For example, it's amplified by packing same orientation of different protein molecules together. They amplify packing, and finally it's large enough to see under crystal. And because protein crystal is shiny and also really colorful. One of my hobby when I was student is I love to take the photograph protein crystal. And here is one of photograph in my first crystal I have ever crystallized. And then after that, we have protein crystal. So our final goal is to get the protein structure. And similar with cryo-EM, we have to photograph it. But the point is, the way we photograph is different with cryo-EM. Cryo-EM, you photograph proteins directly. You see protein molecules look like, how it look like. But in the X-ray, in the protein crystal, because the protein is quite small, we could not directly see the protein molecules. So what we do is we shine the X-ray. And what we photograph we got is we call X-ray diffraction. And how X-ray diffraction look like? This is just the dark like this. And it has a different intensity of the dark. It reflects for information about the protein orientations inside the crystal. And here is actually it's the 3D information, right? So to get the 3D information, we rotate the crystal while shining X-ray beam and continuously collect the data or photograph of the X-ray diffraction. And the more we rotate, for example, 360 degrees, it's a circle. We collect all the X-ray diffraction photograph. It means we have the 3D information of the protein inside the crystal. So what should we do next is we just convert the X-ray diffraction data to 3D information. For example, like this, we have the 2D X-ray diffraction. And then we merge all together. You can remember that we talked about 2D to 3D in cryo-EM. The concept is similar. We merge all 2D information to 3D information. In here, we call total diffraction. It's just a field of the X-ray diffractions. And with the 3D informations, because in the crystal, protein molecules we organize same orientations. So we can able to convert using computational work, convert the total diffraction to the electron density map or 3D map of the protein. And what's next step is definitely similar with the cryo-EM. we had the electron density map, and we built the atoms of amino acid into electron density map. Of course, we had to wear the 3D glasses, playing computational game. And for example, in here, you can see we just orient electron density map. You see the tryptophans, this is isoleucine, and this one is arginine. So you just continuously build the amino acids inside the electron density map at the atomic level. And in the end, you will see, you will build your protein in 3D structure. So now you might ask, why do we need to know or study protein structure in atomic level? Is it important? So to answer the questions, I love to share some my own research, and we can answer in the end. For example, this is structure of the B2H receptor in atomic level I showed earlier. So here is 3D structure. So this is structure in side view, and in here the view is top view. So this receptor is called transmembrane receptor. So they have extracellular domains and transmembrane domains, intracellular domains. Intracellular is cytoplasm inside the cell. And this structure is has 1, 2, 3 molecules. It's a trimerase receptor. And because in the atomic level, we could able to see the molecules inside the structure. So before going into the detail, I'd like to talk about a little bit about the receptor, why we interested in this structure, why we need to show structure of the B2H receptor. So as you know, chronic cough or cough hypersensitivity, there are over 10% of the population on the world suffer chronic cough. This means around 800 million to 1 billion patients on the world suffer chronic cough or cough hypersensitivity. A cough hypersensitivity is there are reasons, and the scientists know that the cough hypersensitivity is because the receptor hypersensitive to binding to ATP. And this receptor is called B2H3 receptor. So the receptor is, when they become the hypersensitive to extracellular ATP, it's easy to binding with ATP, and it opens the gate in the neuron. And when they open the gate, the calcium ion go through the channel into the neurons, and they generate signal. And the signal go to brains, and brains urge to cough. It's a normal case is fine, but because receptor become the hypersensitive to ATP, extracellular ATP always inside our body. So the signal is easy to release because it's easy to binding with ATP. And you cough without reason, cough no explanations. So this one we call chronic cough. So the way to treat the chronic cough is to block the ATP binding with receptor. So there is a drug binding with receptor, prevent ATP binding, so that the channel, ion channel not open, so that no calcium or ions go through into the neurons, so that no signal go to the brains, and cough relief. So it's the concept of drugs for treatments of chronic cough. And so far, a company, GSK company, is investing $2 billion to develop these drugs we call antagonist drugs targeting B2H3 receptor for chronic cough. There are $2 billion to developing a drugs targeting B2H3. So it means the drug market for B2H3 receptor is quite huge, really wealthy. And because we know how drug working, right? The way of drug working is try to binding with B2H3 receptor, prevent ATP binding. So in straightforward way is no structure of the receptor. And this is receptor structure in the atomic level. Because in atomic level, we know well or confidently know how the receptor binding with ATP to open the gate, to open the channel gate. So here is it. This is ATP molecules. It's binding, the way it's binding with the receptor. And we also found that there have magnesium atom in here. The magnesium binding with ATP as well as the binding with receptor. So not only simply ATP binding receptor, but magnesium always go along with the ATP to bind to receptor. And based on receptor structure, we know well where the ATP and magnesium binding is. It's in this location, you can see. And we also know the way how it binds to receptor. And as we look into the receptor detailing, for example, one molecule of the B2H receptor, B2H molecules is a dot. You can see it's beautiful, like dolphin shape. Its head, flock, body, flipper, and head. And we know where the ATP roughly, where ATP binding. For example, in here, scheme, I show you the ATP go and binding in here. And when the ATP binding with this B2H3 receptor, it will cause the conformation change of receptor. So that the receptor will open the channel so that the ion or calcium ion can go through into the neurons. And when calcium go into the neurons, the generate signal go to the brain and cause to cough. So now we know how ATP binding with receptor, as well as where ATP can bind with receptor. So how to block the ATP binding to receptor to open the gate. So we design a drug. And a drug is binding to receptor and prevent the ATP binding. So when ATP not able to binding receptor, drug prevent it. So receptor stay in the we call closed form, or it's not open the channel, so that the ion not go through into the neurons and no signal released. So it's how drug working. So the point is, now how does the drug bound to B2H3 separate the ion channels? How it look like? So to understand molecular mechanisms of the drugs bound to B2H3 receptor, separate the ion transfer. So a straightforward way is again, we need structure. And based on our structure analysis, we see that here is B2H3 receptor binding ATP, and here is channel. And when the B2H3 receptor binding with ATP is closed in these areas, but it open in the entries of the ion. And they also open the gates inside the transmembranes so that the ions, for example, calcium ion, can go through the channel, go into the neurons. And the next is, the signal to cough. to prevent receptor binding with drugs. And when receptor binding drugs, receptor have not able to binding with ATP again, so that the receptor conformation will trap in we call closed form. And this close is, you can see it's open in the top, but the entries of the ion is closed. And more importantly, second step, the gate inside the transmembranes also closed, so that the ions, for example, calcium, not able to go into the neurons, so that it prevents the signal go to the brain or to cuff. So that's the way drug targeting B2H3, preventing ATP binding, stop the cough or cough relief. But based on the structure analysis, we also found something interesting. For example, in the atomic level, we see the gate, and we can measure the size of the gate. And for example, in here, when the receptor binding with ATP, we can see the gates, we can measure the gates around 0.2 nanometer. And look back to ion size. For example, calcium, potassium, sodium. Calcium is around 0.198 nanometer. Potassium is a little bigger, 0.27%. And sodium is around 0.204. So it means the receptor is selectivity for the ions. For example, the calcium easy to go through the gate to go into the neurons. And potassium, it may be limited. Sodium maybe can go through, but a little difficult. Because a different ion go into the neurons, they have a different signal to brain. For example, in this case, is calcium mostly urge to cough the signal from the calcium go to the neurons, for example. And this receptor, the gate is highly selectivity for calcium, for example. But how the receptor binding with drugs? The gate is narrowed down around 0.1. And 0.1 is quite small to all the ion I listed here, right? So calcium, potassium, or even sodium not able to go through the gate to go to inside the neurons. So no signal at all go to brain. And in this size of the molecules, for example, 0.1, it's only maybe water can go through the gate, but the ions are not able to go into the neurons. So this is the principle of the molecular mechanism, how drug binding with B2H receptor stop the cough response or cough relief. So now we know that how drugs binding with B2H3 receptor can prevent the ATP. Then when it prevents ATP binding, it's urged to receptor close the entries of the ions and close the gate so that the ion not go through to the neurons, so that no signal go to brains. So, but more interesting is when we learn about structure. Before that, in atomic level, this is transitional binding of the rocks. Excuse me. It's transitional binding site for drug to prevent the ATP binding. So this one is near the ATP binding site, and we found out that this binding site is quite similar with the other receptor. So it means it drug binding here is able to binding with another protein or another receptor. So as you know, when the drugs, it's not only binding with B2H3 receptor, also binding with the other ones. So it's called we call side effect. So I mean, drugs, if we have the side effect. So the new finding is what we found interesting is the new binding sites in receptor. When drug binding here, also is able to prevent ATP binding to receptor. It's same function, but this binding site is more specific to B2H receptor, more selectivity. So it means if drugs is binding here, it cause less or minimal side effect expectation. It's not binding with another receptor or proteins, so it less the side effect. So it's the final goal of any drugs. Its side effect is a problem. So if we can minimize the side effect, yeah, it becomes good drugs. And because in the atomic level, we know electron density map about the new binding sites. So what next is we're able to design new chemical at a drugs, specifically binding to B2H3 receptor, prevent ATP bindings for cough relief. Yes, and just a short reminds you again, GSK company investing 2 billion to develop the set of drugs. So we're not able to compete with GSK, but we do experiments, we do science what we interest. And in the end of the day, of course, money is important. So now, hopefully, you have your own answer. Why do we need to know or study protein structure in atomic level? Yes, hopefully you have your own answer. So in summary, what we talked today, we talk about the protein molecules, protein structure. As when we talk about the protein molecules, it's quite small. The scale is less than 10 nanometers. And in atomic level, it's around 0.1 nanometer. So, but we have some techniques to determine the protein structure, 3D protein structure in atomic level. For name of fields, we use X-ray, crystallography, we use cryo-EM, and structure we got in atomic level, we can understand how the protein work in the molecular mechanisms. And more importantly, based on structure information, we learn to develop new drugs. So we call drugs guides protein or structure guides drug discovery. And success doesn't happen alone. So all my research journeys have indirect or direct influence from many teachers, many college. And for name of fields, I would like to acknowledge my previous team, called CRISPR team. It's my luck, to have a chance to lead a research team. And also thanks my leadership team in Imnewrun startup. They not only train me, mentor me in science, but they also mentor me to become a leader. So they train me a lot in leadership skills and teamwork. I also would like to thank my previous PIs and college in structural biology lab and my advisors in de novo protein design lab. I also would like to thank you Chang's lab members, Ram's lab members, Purdue cryo-EM facility, and IT. So when we do protein structure work, not only experimentally in the protein, but also, computational work. So finally, thank you all. Thank you for your listening. I'm happy to address any of your questions. Thank you.
Thank you, Trung. This was awesome. What an awesome, awesome lesson in structural biology, in everything cryo-EM and X-ray diffraction. I loved it. I loved it. It's so good.
Thank you, Tom.
I really think you just presented that in such a good way. If you want, you can stop sharing your screen and we come back to being the two on the screen there. It's an incredible journey that you've had, and you kind of went fairly quick at the beginning. And I don't know if other people caught it, but you're originally from Vietnam,
Yeah.
and you went to Korea to do your PhD. My gosh, there must have been a big period in there that you skipped over so much, and I'm so curious about that transition. What was it that inspired you to get into science, and how was it in Vietnam, that period of time in your life?
Yes, actually, I graduated undergrad in the Vietnam National University. And then, luckily, I was appointed as a lecturer in young careers in National University. So I stayed there for 2 years. I got some grant from the Vietnamese government to establish my group in there. And then I realized that, it's different scientist level, honestly. Each time, also the kinds of the opportunities.
Mm.
One group from Korea, they
Yeah.
came to my university to have a talk.
Uh-huh.
And, I interact with the one of PI there. And they said, Trung, do you want to continue to do research?
That's
Yes,
great.
yes, and I said yes. And actually, early time, I don't know structural biology, honestly.
Sure. I mean,
Yes,
that must have been your introduction when you went to Korea to be introduced to structural biology. I really liked, though, the way that I love the house representation. I really thought that comes across well.
thank
Trung,
you.
thank you so much for, sharing with us and imparting your knowledge and teaching us about it, about the techniques, about how we apply those techniques for drug discovery. This has been a real great lesson. I hope a lot of people enjoy this recording. So thank you so much, Dr. Trung Thach from Biological Sciences here at Purdue University, postdoctoral researcher. Thank you for sharing with us in our lecture hall series today. I hope you have a great day.
Thank you, Tommy. Thank you, everyone.
Thank you.
Have a good day.
Bye-bye.
Bye-bye.
Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel.